Okay, so in the last video we talked about measuring the spin of an electron. So now let's try to understand what's the observable that corresponds to measuring the spin. Okay, so obviously this depends upon in which direction we measure the spin. Or in the, if you're thinking in terms of the actual Stern-Gerlach device, it depends upon how we orient the Stern-Gerlach device, which axis we orient it according to. Well, so let's look at different cases. So first, let's start with the simplest case. So let's say that we oriented the Stern-Gerlach device along the z-axis. So remember our convention, we think of spin up as being 0, spin down as being 1. And so what we'd like when we measure the spin is we'd like to say, well, we'd like our observable to be one where the eigenvalue corresponding to this is 1 and corresponding to the spin down state or the 1 state is -1. Okay, so what's an observable which has the property that 0 and 1 are its eigenstates and with eigenvalues 1 and -1? So we've seen this matrix before. It looks just like this. It's 1, -1, 0, 0. It's the matrix that we were calling Z for a phase flip. It's also often called, by physicists, it's called sigma sub Z. Okay? So that's our observable corresponding to measuring the spin in the Z direction. Now, suppose that we oriented our Stern-Gerlach apparatus instead in the X direction. Okay, so now what's the observable corresponding to this? Well, so what are the eigenvalues supposed to be? Well, they are x corresponds to psi sub x is 1 over square root 2, 0 plus 1 over square root 2, 1. And what about the antipodal point? That corresponds to 1 over square root 2, 0 minus 1 over square root 2, 1. And so we want to design an observable which has these as the eigenvectors with eigenvalue +1 and -1 respectively. Okay, so what's an observable which has the property that it has this state, which is a plus state, and minus state as eigenvectors with eigenvalue + and -1? Well, we've seen this before. It's an observable capital X, which was 0, 1, 1, 0. Right? This is also called, again, the physics notation is to call it this matrix sigma sub x. We can do the same thing with y. So now let's say we turn our apparatus in the y direction, and now we ask what's the observable corresponding to this? So again, psi sub y. This state corresponds to 1 over square root 2, 0 plus I over square root 2, 1. And the corresponding antipodal state is psi sub -y, which is 1 over square root 2, 0 minus I over square root 2, 1. I hope you understand what I'm doing. So all I'm doing is I'm reading off the angles theta and phi here. So if I'm pointing in the y direction, theta is pi over 2 and phi is also pi over 2. And so I'm just substituting in here. And then if you have minus y, then theta is still pi over 2 and phi is 3 pi by 2, right? Or minus pi by 2. And so that's how we're figuring this out. Okay, so now we want to figure out what's an observable which has these as eigenvectors with eigenvalue +1 and -1. This is y, which is 0, I, minus I, 0, I believe. So let's see if this works out. So if you do this times 1 over square root 2, I over square root 2, what do you get? So the first entry is you get I squared, which is minus 1, times minus 1, so you get 1 over square root 2. And here you get 1 over square root 2i, so you get I over square root 2. So that's exactly, it's an eigenvector with eigenvalue plus 1, and similarly the other one is an eigenvector with eigenvalue minus 1. Okay, this matrix is called sigma sub y. Okay, so these three matrices x, y, and z, or sigma x, sigma y, and sigma z, these are called the Pauli spin matrices. These are very, very important matrices because they give you the components of the spin in the x, y, and z direction. Okay, and that's a very important thing to understand. Now, by the way, you should really understand that these matrices do not commute with each other, which means that if you measure one, suppose you measure the spin in the z direction, and then you measure it in the x direction, you don't get the same answer as you would if you first measure in the x direction and then in the z direction, right? Well, why is that? Well, this is something that we saw right from the beginning, from our first lecture on qubits, where we said the bit bases 0, 1 and the sign bases plus and minus, they satisfy an uncertainty relationship, right? That if you measure in the one, you're maximally uncertain in the other, and vice versa. And so, in this sense, again, this is a sense in which spin really doesn't act like, it's really not at all like you have this kind of object spinning around an axis in three-dimensional space. The Bloch sphere is, it does give you a correspondence, but then in order to understand what the components are in each of these directions, you use the spin matrices, which don't commute with each other. So if you measure in one direction, it disturbs the answer in the other direction, and vice versa.